Let me give you a bit of my background. One of my big passions is tuning. I tune a lot of different setups. And it goes everything from data modeling itself, but also down to the hardware tuning. Actually going out there, unracking the servers, and actually doing things with the servers. So I sort of cover the stack on tuning. It's one of my passions. I look at a system and I can't help tuning it. Fortunately, they allow me to do that in my job, a lot of that. So it's a big privilege to work with this. I'm sorry, the font is a little bit small. It's not meant to be read, all of it. In 2006, when I joined the CAD team, we did a little cube with 5 million rows per second loading into it, which at that point was the fastest cube in the world. It was a 4 terabyte cube. It had a dedicated SAN to it, which basically means that we had 3 racks of storage to support the cube, one cube in one machine. In the 2007, during a Christmas vacation, I'm a sad character, I'm sorry, I did the ETL world record, and we basically took the Informatica benchmark that had been published on TPCH. There's no such thing as an official ETL benchmark, but what people do is they take the TPCH data set and they bulk load it into whatever database they use, and then they publish that number. It's not a validated TPCH by any means, but that's the closest you get to a benchmark. And we did a terabyte in a little bit more than 28 minutes, which at that point was the fastest. Informatica had a published benchmark of 45 minutes at that point. To do that, we needed 4 racks of storage. I was in the lucky situation that I know the lab manager of Unisys, who has a big lab down in Amsterdam, and they had this wonderful 64-core machine, which back then was a full rack of CPUs. And he dedicated his first, he had a CX380 SAN, and you have a CX380 maybe? It's a very common SAN, it's out there a lot. He dedicated that and said, yeah, you get a free CX380. And I said, no, you don't understand. Your CX380 SAN is not going to be fast enough. I need 2 more SANs to get this number. I have 64 cores, and in order to feed those cores, I need 3 SANs. He said, yeah, but you can get some shared storage. No, you don't understand. I will not share storage. When I'm done with this, your SAN CPUs are all going to be at 100% loading at the same time. If I share any of this storage, I'll see it as a performance regression. I need 3 full SANs to do this. So we got 3 full SANs. That was 4 racks of storage at that point, and machines. One of the things that I want you to take away from this today, one of the key messages is that you are being immensely helped by technology at the moment. Moore's law is just giving and giving and giving at the moment. It's giving in a certain way. There's a certain tuning you have to do to benefit from Moore's law, the doubling of transistor counts. But when you do that, you can get really, really fast. So in 2008, we did it again. That was when the early fast tracks were there. And again, not so important about the numbers here. There's the slides, you can have them up for your reference. We did a terabyte in 10 minutes into SQL Server. And we were able to, based on some of the same setups, we were able to create 25 gigabytes per second scanning out of a single machine. So we could scan a data warehouse at 25 gigabytes per second. And using a similar setup, we had a lot of hardware. Sometimes you're privileged. You get access to hardware, and you go to the vendor and they'll say, we will let you use this hardware for 2 months, but at the end of it, we want you to publish something to tell us how good we are. So that's a good, if you want to do that sort of tuning and you feel comfortable doing that sort of tuning and relatively comfortable that you can get a good number, go to the hardware vendor and ask them for that. They're generally very eager to hear those things. So that's how I typically get access to my hardware when I can't get access to the stuff we have over in Redmond, which is always booked by labs. We did, at that point we were loading, and this was presented at PARS actually in 2009, I think. At that point we were loading into SQL Server at 16 million rows per second. We weren't scaling out, we were scaling up, just had one machine. And all of this was just due to hardware advances. So this was probably a pretty interesting setup. In 2009, I decided that one of the things that I didn't want to do anymore was OLTP. But I wanted to wrap up with some interesting tuning. Today I do data warehousing in big data only. But back then I was still doing some OLTP. And what we managed to do was 13,000 credit card transactions per second in OLTP, which is pretty fast. And that's again a single machine. That's 50,000 transaction log writes per second, if you do that. That's a relatively high transaction log throughput. You're getting about 200 and 250 megabytes per second through to the transaction log at that point. We did this on a 48-core core machine with only 2 racks of storage. What we had used had now shrunk from system. This is actually much more impressive than doing this, by the way. It's much harder to do this. It requires better storage. Excuse me. We had basically shrunk this down. So what we were using now is something that fits about the size of this table and about this height. Stuff got smaller. And in 2010, we took another cube. This was for an investment bank that's running in production now. Case story to follow soon. 6.1 million rows per second was the throughput. Actually, this is not completely up to date. In January this year, we took the same workload and made it go up to 7.5 million rows per second processing speed on the cube. We did this in January, to give you an idea, that on a single box about this size. And that was including the storage. So you're seeing a massive drive towards commoditization and miniaturization. So we were basically able to support 1,000 concurrent queries. And when I talk about concurrency, I mean concurrently executing. So when people say I have 1,000 concurrent users, that doesn't mean you have 1,000 users in your system. It means you have 1,000 users that are all executing at the same time. That's true concurrency, right? Typically what you'll do is you'll extrapolate and say if you have 10,000 users in your system, depending on what system you are, maybe 1 to 10% of those users will actually be doing something at the same time. So this was, we did this on some 2-socket servers too. So a lot of this stuff is, what's going on really here is that you're seeing, if you do things right, if you get your tuning done right, you are seeing a massive boost in performance for almost no money. Performance is becoming very, very cheap. Did a lot of Cube. Anyone here has read the Analysis Services Operations Performance Guide? Anyone who works with cubes? Okay, so those of you who didn't put up your hands twice, you need to read those documents, right? Because those are documents that describe how to tune your cubes. And they're freely available. You don't have to pay for them. You can get them from Microsoft.com, and they describe in great detail how to tune your cubes. They are currently out there. There's an R2 version of both. This is wrong. It's not soon to be released. This is released. So you can get the R2 version. And in case you were wondering, this applies to 2008 and 2005 too. This, by the way, is another key message that I want you to take away. Because you're trained in SQL Server 2005 and you go to 2008 R2, you don't need retraining. It's the same thing, right? Training to a new version of SQL Server is 99% of what you already learned you can reuse. That's a central point. If you're a good DBA in 2005, you're going to be a good DBA in 2008 R2. And on 2012 too. There will be a few more things you need to adjust to, and we can talk about, for example, column stores, which I have some slides on. Anyone here played with column stores in CTP? One. Anyone here knows what a column store is? A few more. I'll talk a bit about column stores, because I think that's a very cool feature you need to be aware of. So that's the 1% improvement from the DBAing from 2005 up to now for the warehouse designer. Warehouse design is very similar, but from 2005 all the way until now. Very similar things you need to do. There was some Maestro training there too. I'm not going to dig into that. But I am going to dig into, because this is, after all, this is a presentation about scalability. So I'm going to talk a little bit about scalability, what it means. So I've shown you a little bit about some of the numbers you can get out of SQL Server if you do it right. But typically that's not where the conversation starts. The conversation starts with a customer who says SQL Server doesn't scale. How many of you have had that conversation? Oh, you're very lucky here in Sweden. I get that all the time. And again, it may be perception basis. We get flown into some crazy customers sometimes. And they will say, it doesn't scale, we don't trust it, blah, blah, blah. You have this conversation. And I don't really think that's a conversation we need to have in most cases. There are truly cases where scalability is hard with SQL Server. I'll tell you that right away. But most of those cases, you are in the 0.001% if you're in that space. And I'll show you some of the places where that hurts. What people mean with scalability is many things. Right? There's not really a single definition of what it means to scale. It's something that especially CIO types are really happy about saying that. They'll go out and say, does it scale? And then they look really smart. And like, I know what I'm talking about. But most people actually don't know what they're talking about when they're scaling if they're at that level, right? Because if you say, does it scale, you have not said anything. It's a completely hollow statement. You need to describe what does it mean to scale. In what way? Does it mean that you need to have a lot of concurrent users? Because I can tell you big data scales really, really well with a lot of data. You try to put a lot of concurrent users on a big data Hadoop system, it doesn't scale very well. So big data, as everyone talks about, is the ultimate scalable thing. Yeah, but try to put 1,000 users that are all executing at the same time and it won't scale anywhere. Store huge amounts of data is another good. So storing data is not hard. You can take a single machine and you can hook up a SAN or you can hook up direct attached storage. It's not a problem to put a petabyte of storage on a single box today. It's perfectly doable to put a petabyte of storage on a single machine. Yeah, you need a few PCI slots, you need some HBAs and you need some routers and switches, but you can do it. It's what you do with the data that's interesting. Storing data is not hard. It's how do you administer that data? How do you back it up? How do you access the data? If most of your data is historical, like for example the cube we were doing, some of that data they wanted to keep around. They had 4 terabytes that hot, where there's constantly users accessing it. You can almost squeeze that into memory in a modern machine. And then they had a lot of old data, like 20 terabytes of old data. They're putting that on some cheap storage, and that's fine because it's never being touched, that data. So we're handling the data storage by partitioning data. So storing lots of data is a different problem, depending on what you do with it. Then, of course, you need to be able to query it. Do you want to be able to query 20 terabytes of data and get response times in less than a minute? You can do that. Do you want to pay for it? Is that your real requirement? Or is your real requirement actually that maybe 1 terabyte of that data, let's say you have 20 days of data, and 1 terabyte of that data is really hot because it's the latest day and everyone looks at that, and you need to query that in less than a minute and you can live with it half an hour for the other one? Your price just went down. Not defining scalability has a cost associated with it. So that's why you need to engage in a conversation about what scalability is. Because there's no universal scale machine. I know that Oracle Exadata wants to sell that to you and Teradata too. But you try to put OLTP on Teradata and that won't work very well. And you try to put a big data warehouse on Oracle Exadata and you better be damn careful about how you partition that thing. So scalability is something that has to be defined. Of course, there's the entire development cycle too. I don't count this as scalability. The other thing this is about data warehousing, this presentation today. I'm not going to go into that. So the slides are, again, we can jump around a little bit. This, I assume, should be, how many has a warehouse here? How many has an OLTP system? How many of you don't run SQL Server? So what do you have the rest of you that don't have warehouses and OLTP systems? Free text indexes? Or you're just falling asleep? Okay.
But I mean, in case of consultants, they can't say that I have.
Work with it then. Okay, sorry, that's right.
Yeah.
You who has worked with the data warehouse? I'm sorry.
We don't own them.
Okay, that's a much bigger one. Good. So this picture should be relatively familiar to you. This is the Kimball picture of the world, right? This is what it looks like if you're a Kimball warehouse. Approximately. There might be more of these, but approximately this is what a data warehouse in a Microsoft Kimball world looks like. There's some source systems you connect with some drivers. We know we can do this really fast. I'll show you how you can do that fast if you want to talk about bulk loading. You stage some data. Sometimes that's transparent and magic and you don't stage it at all. You'll discover that when you get a lot of data that won't work. And you get some business logic, you get a relational data warehouse. And that's typically a star schema in here. And if it's not a star schema, you typically end up with some interesting problems. And then you build a cube on top. So that's sort of the high-level picture of the relational data warehouse. This is what I call the back office of the warehouse. This is where all the computational problems happen. This is where we shift data around and we store data. That's where the scalability typically is. It's here. And then there's another part of the data warehouse. And the reason this slide is here is because I don't want to talk about it after this slide, which is how do you get from the data to the end user? This is a very interesting problem, and there's a lot of usability involved in this. There's a lot of analytics involved in it. There's a lot of different client tools involved in it. It's a very interesting conversation to be had about this. This is what we traditionally call BI over here. Some people will include this one over here in BI. I call it the data warehouse. This is just another way to represent a database. But traditionally, at least this is, I think most people agree, is the BI part of the world. I'm not a BI person. I don't deal with client tools. As you can probably guess, I'm not a good person to put in front of people who like client tools. So I'm not going to talk about BI today. For BI, I would recommend show up on the second. Akshay is here. Akshay is super sharp with BI. So he will be able to get you a lot of those answers if you're looking for answers in the BI space. I will talk about the first thing, namely this one. So that's a bit of setting the stage for today. And in case, any questions at this point? Anything you specifically you want to hear about in this space? So that I'll be sure to cover it. If not, just interrupt as we go along. I want to return a little bit to the Moore's law thing, because this turns out to be a very important observation. Does anyone here consider themselves a logical data model? Do you think about data modeling as logical and physical modeling? Good. Because I think that's a waste of time. The reason is that you can't logically data model something unless you know something about the hardware you're running on. It's a little bit like trying to build a building and not knowing how strong concrete is. You can put a nice architecture in there and you can draw the building and it looks pretty and it looks nice and you can win a design reward for it, but you can't build it if you don't know what things are built of. And the same is true for computers, and the same is true, especially if you want to drive costs down, which is very, very relevant these days. Everyone talks about driving the cost of computing down, and you can drive it down quite significantly. Here is the Moore's law. I assume everyone's familiar with it. Basically says every 1.5 years, the number of transistors double. So basically, you see the transistor count going up every year, using a logarithmic scale over there on this one. This is because we're shrinking all our devices and components, and when we shrink them, we get more out of them. We get more cores and we get more clock speed. So that's the law we're living on. This is not a law in the sense that it's a physical law. It's an observation about how engineering currently works. There's this interesting trend that making a breakthrough discovery is an unpredictable event. The invention of the transistor, for example. We don't know when the transistor is invented, but the moment we invent something, it's relatively easy to extrapolate from what we've invented to where it's going. Because engineering constantly makes improvements to things that are invented. It's hard to predict when we invent them. So Moore's law is a prediction about engineering. And it's true, it holds. It actually, even today, this is an old graph, I'm afraid, but this holds even up here in 2012. We are seeing this doubling. It's continuing. We are getting better and better at shrinking our chips down. That's why you can have devices like an iPad and an iPhone, and you can have a computer in your pocket today because of Moore's law. What Moore's law does not say, and this is a very important observation that will be immensely relevant. It is immensely relevant, but it's going to be even more relevant now. It does not say that your bad code is going to run faster because time goes by. Moore's law says that you will get more transistors in the same device. It doesn't say that your clock speed will go up. It used to be true, if you look at the bottom of this curve, around 2005, up until 2005, it used to be true that every year, every 1.5 years, the clock speed of a CPU went up. Those of you who had computers early will probably remember that we had 386s, and we thought that megahertz was a really good number, right? And then we got up and now we got gigahertz. And some of you may even have an AMD Opteron at home still. And an AMD Opteron runs at 4 gigahertz. That's a pretty old machine. There's no 8 gigahertz computer out there today. Even though Moore's law should, at this point, have created an 8 gigahertz computer. And the reason is that you can't keep synchronizing these things. You get more transistors, but what do you get for those transistors? You get cores. You don't get speed. This turns out to be very important for how you develop things. Cores are cheap, very cheap. Speed is not cheap. So when you talk about cheap computing, it's about many cores. It's not about a lot of clock speed. This has some interesting consequences. The key takeaway here is that clock speed is not going to increase very much in the future. About 4 gigahertz is where we're stuck. Do you know how long electricity travels in one clock cycle of a 4 gigahertz stroke? About 25 centimeters. This means that modern computers are now designed in a way where the memory, the bus to the memory, if there's a turn on that bus, the inner lanes will be twisted to make synchronization easier, because the distance between the CPU and the memory has become an issue to synchronize. That's the type of loss we are fighting at the moment. That's what computing is. That's where computing is going. And whether or not you like it or not, that's what you're going to have to run on and optimize for. Fortunately, something else has happened in the last couple of years that really help us. Traditionally, we have been stuck with these spinning metal plates, metal frisbees. Very slow, cheap for space. You can get a lot of space from such a hard drive, but it takes a long time to find something on it. Typically up to 8 milliseconds if you're running SATA. 8 milliseconds is eternity for a computer. In 8 milliseconds, you can have a lot of CPU cycles. So if you can't feed your CPU fast enough, you're not really getting anywhere. Sequential access, we've spent a lot of time optimizing for sequential access. When we talk about fast track installations, anyone here has a fast track? Anyone knows what it is? A few more. Fast track is a reference architecture that Microsoft has produced that allows you to basically build very, very high scan speed installations at very low cost. And one of the things that they use is the fact that sequential access is fast. Because what takes time on a hard drive? If you have a hard drive and it's spinning around like this, if you're staying at the same spot and just reading things that are next to each other, you can read them at about 125 megabytes per second on a single disk. If you need to move that pickup back and forth on the disk while it's spinning around, suddenly that number goes down to, depending on how large blocks you read, 3 megabytes per second. So this enormous optimization has really helped us. And we spent a lot of computer cycles, a lot of engineering, a lot of effort over the last 30 years getting good at this. Unfortunately, all of that is now not relevant anymore, or it's going to be very soon not relevant anymore, because we have a new kid on the block, which is NAND devices. Anyone here runs a NAND device SSD? Anyone has that in some of your servers? It's a bit of a different experience, isn't it? It completely changes the equation. NAND devices are fast by default. They're a little bit slower to write than the traditional disks. They like these type of multi-threaded query patterns that we traditionally associate with memory. So what we like when we want fast memory access, we don't want to say fetch memory, do something with it, fetch memory, do something with it. We want a lot of threads that are all going to memory at the same time. So that's traditionally how we think about memory. Go multi-threaded into memory. With these NAND devices, the SSDs, they have the same behavior. They like a lot of CPUs working at the same time, going after the same data, the same devices. If we do that to a traditional hard drive, that's going to completely ruin our picture of the world. That will slow us down a lot. So the programming we've done on traditional hard drive, all the time we've spent optimizing for traditional hard drives, we now have to sort of reverse some of those changes and start treating hard drives like memory, because that's more what they're like. These SSDs are not hard drives anymore. SSD is, so let's say, drive. Well, it's not really, drive is not really the right word for them anymore. They are solid state memory. And you have to treat them as if they were memory. You can still get SATA, and I suspect we'll see SATA hang around for some years yet as backup devices. But if my predictions are true, I think we'll see these NAND devices pretty much take over the next 2 or 3 years. So we better get used to them now, because they're quite interesting to tune for. To give you an idea of what we're talking about here, this is a single Fusion I/O device, one of the vendors in the market. And as you can see here, as I go down, you see the queue depth here, that's how much is outstanding per thread. As I decrease the number of outstanding I/Os per thread, which is traditionally a bad idea, my throughput goes up. I have the same number of threads, right? In this case, 256. So I decrease, my throughput goes up. As I increase the queue on each thread, which would be great for a traditional hard drive, my throughput goes down, and my latency goes up. This is 250,000 IOPS out of a single PCI card. You open your server, you plug it in, 250,000 IOPS. To give you an idea, that's about the specification of the biggest SAN you can buy. You go out in there, you spend $10 million on the biggest SAN you can get, and you get about this number. This is $25,000, you plug it into a machine, and it just gives you that number. No configuration, no thinking involved. That's a big shift, and that's really going to change the way we think about computers and data warehouses. Right. I don't want to talk too much about this. Anyone want to hear about cloud? No, good. The one thing I want to say from this slide is there's something called Numa now. Who here has a Numa machine or has worked with a Numa machine? Who here has a 2-socket Westmere or Nehalem machine? Who here might have one, but I'm not sure. Okay, so this is going to get important. How many of you have worked on a machine that had more than 2 CPU sockets? 2. Okay. Let me give you an idea of what a 2 CPU socket machine is today. A 2 CPU socket machine is about this thick. And it's about $20,000. On a 2 CPU socket machine that you can get for this peanut money, you have a Numa system. You can't buy a 2 socket today that's not a Numa. Any new machine you buy is a Numa machine. What is Numa then? Numa is short for non-uniform memory access. And let me talk a little bit about that, and then I'll get away from hardware. Let me just find. We can jump around a little bit. Security, protect me from unknown content. That was not known. This is what a big box looks like, and you can scale this down to smaller boxes. You have Windows. Windows has something that's called kernel groups. This is a new concept in 2008 R2. Kernel groups, in most situations, if you have typically less than 40 cores, you have one kernel group. So this is typically not something you have to worry about. If you have more than 40 cores, if you have a 4-socket machine, for example, that will have 80 cores, logical cores today, then $40,000 piece of hardware, you'll have 2. Normally, you don't have to worry about that. Let's say you have one kernel group. In the kernel group, you have Numa nodes. If you have more than a 1-socket machine, you will have 2 Numa nodes, 1 per socket. If it's an AMD, you'll have 4 Numa nodes. If it's an Intel, you'll have 2. These Numa nodes, if you scroll into those, contain CPUs, CPU cores. Typically, the Numa node will either map to a socket or part of a socket. And inside those CPU cores, you have hyperthreads. If you're an Intel, if you're an AMD, you just have more cores. The interesting thing about this is that when you look at how these things are wired to memory, this particular socket has its own cables going to memory. And this socket over here has another set of cables going to memory. Going across from one socket to another can cost you a factor 10. So if you're talking to, if this one talks to memory on one socket and has the memory sitting over here, and it needs to get to some memory that's owned by this one down here, it will have to interrupt this CPU if it needs to write it, and it will need to go to that memory. That will burn CPU cycles, and it will burn time. If you buy a blade server today, you have this problem. You may not know you have it, but you have it. So this means that Numa is something we're just going to have to live with in the future. Going past Numa node is going to be something that we will have to start designing for. And when you design data warehouses, having this in mind helps you, especially if you want to do high-scale loading stuff. Okay. So how can we measure that? Actually, there's a tool. If you go to SysInternals, which I, by the way, highly recommend, it's a great library of tools that you can use to learn about how Windows works. You can actually download something called Core Info, and Core Info allows you to see if your Numa node system is set up correctly. And it also allows you just to get an idea of what your Numa system is like. So what it measures is it gives you a matrix, and it gives you an approximation of how expensive it is to go from one node to another. So for example, you see this one here, Numa node 01 talking to Numa node 05. is 10 times slower than if it goes to its local memory, approximately. Now this can happen in, for example, some machines nowadays are cabled together. And if those cables aren't set up right, or if the patches of the system are not applied right, then this becomes 10 times slower. You get a 10 times performance drop when you go to the foreign memory. That 10 times performance drop can end you in situations, and this actually happens a lot these days, where you go in there, you have a big system, let's say that you're 100% CPU. You want to add more cores. You add more cores to them, but your Numa isn't set up right.
Thomas, just a question. If you look at from Numa node 01.
This is completely messed up, this system. This is an unpatched system. You see this one gets better.
Yeah.
This system over here is messed up. This is patching, hardware patching that's missing. This one over here is much better, but still not exactly as wanted. So you see, actually just talking to your own memory has different latencies depending on which socket you're sitting on. Somewhere around here there'll be a 1.1 there. Right? So this one seems to behave the way it should be. Everything else is just off the charts. And what will happen very often is that you go out there, you run on the 2-socket machine, you're happy about your throughput, but you need more users. So you go out and you buy a bigger box, right? Double the money, double the sockets. And what you discover is that when you move to the bigger box, you run slower than you were in the smaller box. This is a very common experience. People go out and they believe they can throw hardware at a problem, but actually what happens is when they throw out hardware at the problem, it gets worse. This is not a very good situation to find yourself in if you just put in a budget request for a new machine. So we have to learn about these things. We have to understand how they work and how Numa works. And we can talk about how SQL Server does that. Just to give you an idea what such a box can look like. It can look like that in Task Manager. So we can get some pretty big boxes today. Okay. Let's see. Let's see just a second, sorry. I'm gonna have a lot of slide decks. So what are we trying to get to? We know that we have hardware that's becoming increasingly complex but also cheaper. We get very fast storage. I/O is not a problem anymore. I can build a system today that does not have an I/O problem. And I can build it cheap. That's the trend. That's where we're going. Buy a Blade server that has 100,000 IOPS in it. This means that we'll be able to run a lot more on smaller hardware. What we want to do is, ideally we would like a scale curve that as we add more hardware resources, we get faster, automatically. That's the type of design we want. It doesn't really matter whether you scale up or you scale out. You want a design that looks like that. If you haven't achieved a design where you can throw hardware at the problem to make it faster, you haven't achieved scalability. Very often, if you do nothing, this is what it will look like. You'll actually get negative scale as you add more hardware. And quite often, you get some sort of flat line. There's a point where it doesn't scale anymore. So a good example of this is if you try to build indexes, for example, on a non-partitioned table in SQL Server. And you have a 48-core box, an AMD box, for example. What you will see is that there's some point around 24 cores working at the same time where this curve goes flat, where it doesn't scale anymore when you build the index. If you build it on a partitioned table instead, and build 2 indexes at the same time, it will continue to go up. So you can cut your index build times by partitioning, for example. The same is true for some types of queries and some types of loading. So you can say, well, it should handle that automatically, shouldn't it? And there's a lot of things that we can't handle automatically unless we know what you're trying to achieve. And there's also a max amount of parallelism you can throw at a problem before you start getting diminishing returns. And then it becomes the data modeler's problem to model the database in such a way that you take advantage of parallelism. So this is the sort of common type of problem. I think I've scared you enough. And for some reason this won't switch. Come on there. Here's what we don't do, right? We don't observe that it's run slow and just start randomly changing things. I will argue anytime to you that tuning SQL Server is an exact science. There's no guessing here. There's no art of tuning. There's an art of data modeling, but there's no art of tuning. Tuning is exact. You can measure everything, and all the dials are there. All the stuff you need to measure is there. So we shouldn't be doing this. Root causes and instincts sometimes help you, sometimes they don't. They're sort of a bit unpredictable. Instincts tend to become better as you tune more and more, but in general, we should avoid these tuning bottlenecks. And I mean, my favorite one is you see hoof prints, you should think horses, not zebras, unless you live in a zoo. And some organizations resemble, I would admit. So what I do is when I tune, I apply a strict scientific method to tuning. I generate a hypothesis, what I think is wrong. This is where the experience comes in. I say, what do I think? Based on the data I have, what is most likely to be the problem? In order for me to make that prediction, I need to know how SQL Server works and how hardware works. Because if I don't have a picture of what's actually going on in the system, if I don't have a model of the world, there's no way I can come up with a prediction of how to improve it. And this can go way beyond, traditional just index tuning stuff. We're talking about things where you're really pushing hard for this. You change one variable, you run your measure, you compare, you discard if you don't or accept the change, and you continue like this until you break it. You need to always, of course, agree with people what your scalability target is. I mean, open-ended tuning is fun, but rarely very profitable. And you should basically engage in this loop. And you can get really fast at looping through these things. You generally want to have an environment where you can play around with these things if you're really serious about tuning. If you're not allowed to touch anything, you're reduced to guessing, essentially. So you want to have some luck. And I realize not everyone has the luxury. So when are you done? Well, tune it till it breaks and then break it and then fix it so you can break it again. You're done when all your CPUs are at 100%. And you don't believe you can improve your algorithms anymore. That's the ultimate tuning. You may not need to be at that point. Maybe you're fast enough at some point. But running a machine that runs a batch load in the middle of the night in a data warehouse workload, and you're running it at 30% CPU because your DBA thinks that that's a good number, is a waste of hardware. Right? If you're running your CPUs at 30%, you have a bottleneck somewhere, or you're not pushing the system hard enough. Maybe it's not relevant. Maybe you're fast enough and you don't care, and that's fine. Buy a smaller server, you're wasting your money. But running your system at 100% CPU, then you're really truly pushing it. You've removed the bottlenecks. And you may even also have improved your algorithm so you can get more done with that 100% CPU. It is perfectly viable to get to 100% CPU in a tuning scenario. And that's when you don't have the bottleneck anymore.
But in a lot of situations, you need a lot of time. So if their systems are running 100%, that's a worry for them.
Yeah.
Oh, my system.
If you're an OLTP system, and you're 100% you're worried about that, I understand why you can worry about that. You're an OLTP system, you have 1,000 users that are currently active on the system, but you know that every now and again you have a spike to 1,500. At that point, you want that spike to be covered. So you want to have some spare capacity. If you're a data warehouse, why would you not run at 100% all the time? If you're a data warehouse and a user sends a query and somebody else comes in and sends a query, they can share the CPUs. They'll get half the response time each. But if they're not running at 100% CPU, you're wasting your CPU cycles. These things are expensive. So if you're clocking your system at around, say, 50%, you're not really making use of your hardware. And one of the goals of many of the fast-track tuning techniques is exactly that. It is to create a system that is balanced in such a way that your CPUs can always run at 100% if you need to. So it's like having spare production capacity you're not using. So I hear this a lot. What should my CPU percent be? Well, if you're perfectly fine with getting the fastest response time as fast as possible, it should be 100. So that's something to consider when you're tuning. Let's see. Here's what I always collect. So this is how I approach this thing. I always want logical disk. Everything from logical disk. Is my sound working? Okay, good. The logical disk counters, they're very low impact to collect. Just get them. The network interface, I want to see all of that too. So when I'm looking at this, I'm looking at what are the basic building blocks of my system and how are they performing. I want this. I want this. I want my processor. I'm especially interested in this ratio. If I'm tuning something .NET that people have, where they've written their own code, you will very often find that they spend a lot of time in privileged time. That's very often wasted. So if I'm tuning .NET, I want something like that. And I want each process in the system. This is a perf collection you can run non-stop on your system with almost no impact. You need disk space to store the data, but collecting this data is very, very low impact on the system. This is a minimum baseline. You need this in order to say anything intelligent about a server. That's not a guess. Here are things that you may want to get as you learn things. You want the XPerf. Has anyone here run XPerf? I know you have, Johan, but who else? So XPerf, does anyone here code .NET? All right. Anyone here run systems that are really, really sort of deep into SQL Server, where you really want to dig in and truly understand what's going on in the belly of SQL Server? That's why you're here, probably. XPerf is your friend. This is the tool on acid, the ultimate tool. XPerf, think of it as a profiler of everything on the machine. Think of if you could hook SQL Server Profiler into every single thing that goes on in your box. That's XPerf. It will tell you which function calls are happening inside SQL Server. It will tell you where Windows is spending its time. If you have a process that's doing some I/O and you don't know which process does that I/O, XPerf will tell you that. If you have a process that burns CPU, but only every now and again, XPerf will give you that information. It's a very, very cool tool for this. This is really, if you really want to understand the workload at a deep level, XPerf is just great. It will only work on 2008 and plus. It won't work on 2003. For 2003, you need something that's called kern rate. And if you're a Unix guy, you'll probably think that that's cool because it has a command line that's this long. But it will collect about the same information. But XPerf is really a very user-friendly way to do it. I'm not big on demos, I'm afraid. But I think I have some XPerf dumps. You want to see an XPerf dump? Hands up. Yeah, you want to see an XPerf. Just.
Okay, 10 minutes, Thomas.
I got 10 minutes. Oh my God, I'm running out of time already.
Then it's just time for a coffee.
Okay. Let me see if I can find a good one. So let me just show you what I'm doing here. I run XPerf and I run it on, XPerf is a command line tool and it just basically dumps a data file. It's called an ETL file. It's nothing to do with ETL in the traditional sense. That's just the extension you use. And then you start XPerf like that. Let me just see if that works. It does. This gives you an interface that looks approximately like this. And it will take some time. A warning. If you run XPerf on a server that's busy, let's just take a 2-socket blade server, and it's about 100% CPU and it's doing some work, and you're running it with the default parameters that I generally run, which look like this. I will do this. I'll say XPerf on latency, stack walk, profile. You can look this up in the XPerf manual file. This is my basic trace. It basically says, give me everything that's waiting for something, everywhere, and give me the call stack of everything that executes. You run this on a 2-socket server that's busy at 100% CPU, and you run it for about 10 seconds, and you got a 30 gigabyte file. This is not something you're going to be running in the background in production. It generates an enormous amount of data, and it likes to use memory while it does it. The CPU impact of tracing is very, very low, and you can control the memory impact. But it's not something you just want to throw at your production server. You just want to experiment a little bit on your laptop first and find out how it works. Because if not, you're going to be in trouble. There will be do you have the notion of wait for the screams? Do something in production, wait for the screams? So here's what XPerf does. Unlike WinDBG, which is the debugging tool for Windows, this one actually has an interface that's understandable by mortals. And WinDBG uses magic. So this is what it generates. It generates something like this. It can generate a lot of other things. And there's a lot of information obviously here, but let's look at some of that. This one is particular I like a lot. This is the CPU sampling that says, for every CPU in my system, what is that CPU doing? And how much time does it spend doing different stuff? And if you're really curious about how it is, you can actually see the breakdown by CPU. If you want to look at a specific CPU in the system, you can actually look at that CPU. So you can see this is from a nice little system here. And then you can do this, and this is just complete techno. I won't say the word. So you go in here and you say summary table. And let's see if I have this set up right. I don't yet, but I will, just a second. So I'll forget to do this. In here, there's a function called load symbols. If you're doing this on your laptop, find a good big directory. It's going to take some space. It requires a bit of hard disk space. You configure your symbol paths. They can be set up in different ways. This is a default symbol path with some tricks that I play inside Microsoft. But you can set the symbol path up, except for that one. I have a blog about it on SQLcat.com. You just search for debug SQLcat. You'll find it there. And anyone, should I send some notes out or something after? Yeah. Don't take notes. We'll send if there's any questions. So you set this up, and basically what it does is it goes into this file, and it analyzes it. And again, this is not just SQL Server specific, so I'm just getting carried away here. It goes into the file, it looks at the offsets of every single process that's loaded in memory, and it samples those offsets. So it looks at it and says, let me find out at this particular point in time, where is the process in memory? And the symbol allows you to take that offset and map it back to the function name inside the code. Ta-da! What does that mean? Let's see if we can make it work. Did I check load symbols? I didn't, because I forgot again. For some reason, this is not default. I don't know why, but it's not. Again, people who design debug tools are not great user interface designers. This is a great step forward, I should say. This, by the way, is available from the Windows Performance Toolkit. That's a free gigabyte download. This one is 100 kilobyte executable. You have to get all of it. Sorry. So you just sort of copy it around on your servers at some point. You go simple summary table. That was better, right? So now when I said solution, so you can see here that this is a system, this actually is a rollup system where the analysis services is querying SQL Server in rollup mode. And you can see that the CPU distribution between the two servers is about 50-50. So there's nothing new here, we know that, right? Because we can use the process counters in perfmon and see the same information. That's not interesting. What's really interesting here is, let's just get the analysis services because this one's special. Is we can see, and when we expand this, we can actually see inside analysis services which DLLs are being activated. So if there's a DLL that, for example, we can see here that SQL OLEDB, for example, that's the OLEDB connection between analysis services and SQL Server. And we can see if somebody says it takes a lot of time to do the OLEDB, we can say no, that's not the case. Look, OLEDB is actually very cheap. What it looks like is that it's inside analysis services. And interesting, there's a kernel time here too, right? NTOSKINL, you get to learn them in your head if you play with this at all. This is the kernel of NT. So now we're seeing that analysis service inside the process is calling into Windows. So we can see the call that happens. But it gets better, right? Because we can see the function call in Windows. This is the Windows source code. The function call inside. You can do this. This is you can't see the lines and you can't see the actual source code, but you can see the source code. You can actually see what happens inside Windows. So you can see that, for example, it spends about 2% of all of its time doing memory copy operations. For those who run .NET and who like to allocate and garbage collect and all that stuff, that's just wasting all your CPU cycles. You can see how much they waste now. So you can quantify the CPU wastage. You can see that, for example, the walk frame chain, this is some debug stuff. All of this you can search for, and you can look at the Windows internals book. You can go into analysis services. So all of those who think that, we can't look into analysis services because it doesn't have all the instrumentation of SQL Server. No, but it can do this. Right, we can go in here, we can actually, you can do this. You can see that most of the time, here you see that 9% there, half of the time is spent on calling into something called MDD code implementation. Now, we don't really know what that is, but look, if we do something, we might actually get an idea of what that is. Because if we, instead of use summary table, did we do simple summary table? We should be able to get it. Let's see. Roots. Oh, yeah. So what we do here is, So what we do is here is, instead of looking at the individual function calls, now we group them by how we got there. So now we're grouping by what was the sequence of events that led to that function call. So this is the stack. We're basically walking the stack, and we're unraveling the stack, and we're bucketing the stack inside it. So we can go in here, we can actually see, so we can see that, oh, we start a thread. That's not surprising. Here's some SQL DLR here. Let's see, where's the analysis services? Where is this? Here we are. Here's the decode implementation, yeah? You saw that one? There we see, we can go in here, and you can see that there's some mem copy going on, and we can quantify what it's doing here with the mem copy. And you see how, so here's it calls the mem copy. You saw that mem copy we did inside the kernel here? Yeah, you see there's, oh, that wasn't expensive. Let's see if we can expand more into this. Unfortunately, we couldn't on this one. This trace doesn't have it. But if not, you would actually see that inside decode record, there would be a read file call. And decode record is actually the function inside the analysis services code that reads the file from disk. So we can now see that 10% of our CPU is actually spent on reading files from disk. And we can see that how much of that is broken into the kernel time and how much is broken into the analysis services space. So that information is not in this trace, I'm afraid. But that's sort of the detail level you can get to. And it gets better. It can do all sorts of cool stuff. It can go in here. And I'm sorry, it's almost a sales pitch at this point. You can go in here. This is the IOs. Every single IO that you do in the system, you can see here. Not this logical disk file. This is details, real details, right? This is the kind of stuff where somebody says, somebody is reading my disk, I don't know who it is. But it's IO and I'm tired of it. Let's go in there. Actually, let's just get, oops, no, that's not the one we want. Let's see. There's so much information in here that's just crazy. You can go ahead and say, let's get a summary table. Here we are. Hey, that's a SQL server that's spending our IO. And here you can see that it's doing the database activity in TempDB. So you can actually see where it's doing it. And you can see that it's writing down to some file in here that's called performance log. And you can see, let's see if we can, and you can see how many reads it did in there. But it gets better. You can actually see individual reads. So you can actually see how many reads and how many writes did it do in there. This is the kind of stuff you pull out of virtual file stats in SQL Server. There's a view that you can look in this. But in this one, you can see every one of them. You can actually see if you had an outlier. So if you see here, you can see here's every IO. Every single IO request that was issued in that time frame. You can actually see it, and you can see how long did that particular IO request take. So if you have a SAN that has a crap cache, because SANs often have that, you can actually see that you have spikes, even though they don't always show up in the averages. You can get into that detail here. This is the ultimate tool, right? Learn to use it. It's a bit obscure in the beginning, but the amount of information you can collect it. If you have .NET coders, you don't need to know their code. You just need to trace them with expert, and you can see what they're doing. What you should ask them to do is you should ask them to compile symbol files. It's something you said in Visual Studio. You said, I want the symbol file. It generates a little file called PDB, and that file you need to have as part of your XPerf directory, and then that allows you to see exactly what functions they're calling. So this is sort of, we're going out on a tangent here, but I'm very fascinated by the tool. I use this tool a lot for tuning. Every time you have something that's close to 100% CPU, you can really get into where you're spending your time in a way that's no way possible to quantify in other ways. All right, let's see, that was XPerf. Are we having a break?
Yes, so let's just wrap up if you want to.
Yeah, so basically, I just want to finish up what sort of, yeah. I just want to talk a little bit about the basic collections, and then we'll, So Xevents is essentially the same interface that XPerf is using. So you can get that inside SQL Server. In 2012, you can get it in analysis services. You can get something called mini-DOMs. That's more detailed. I won't go into that. And there's a few stuff here. For example, waiting tasks is very good to get. So there's some stuff that you can get here. Core info is always good. It gives you information about what system you're running on. And of course, what you want to do is you can use Management Warehouse to collect this. And I know that a lot of people think that that's cool, and I like it too. It's great. The problem with Management Warehouse is it's not very portable. So anyone using Management Warehouse? No, good. So you can basically use a perform collection. You can set this up from the command line. I have a little command line that I use, and I basically use this. And I distribute for people who want it. I have a Facebook group that's called Real Men and Women Use Command Line Tools. You can do this thing. You can basically just sort of put it all into a nice package and put a zip archive, and you can move it around between servers. So if you're into this sort of performance tuning, I would highly recommend you automate this, and I'll be happy to share the tools that I use. That is a good coffee break.